Good evening, May 24th, 2023. Well, since yesterday I was talking about largely the orthogonal functions and the standard and the classical orthogonal functions and the standard and the non-standard sorts, and the idea of some higher dimensional orthogonal functions, and some ideas that can get into a kind of a fuller sort of differentiation, then there's been kind of discussion about the ideas of the geometric and the analytical and these kinds of things. So I thought I'd get back to the Fourier analysis, seeing where I read off here, for example. If we recall the well-known formula, integral from negative pi to pi of cosine mx dx equals 2 pi if m equals 0, or 0 if m not equals to 0. Is it symmetrical, or it's 0? So with regards to how it's contains or doesn't contain anything. Integral from negative pi to pi of cosine nx cosine mx dx equals pi if m equals n, and 0 if m not equals n. And integral from negative pi to pi of sine nx cosine mx dx equals 0. So this is kind of this basic expression about the second form of the orthogonality of it. So it's talking about the coefficients of the Fourier series. The main question is whether or not a given function f defined in an arbitrary interval alpha minus a, alpha plus a greater than 0, can be represented by the sum of a convergent series of trigonometric functions. Actually, we can reduce this to a somewhat simpler problem. Given a function f from negative pi to pi onto r, is it possible to determine coefficients a sub n, b sub n, such that fx equals 1/2 a naught, and this is a naught and b naught are kind of combined. And then the sum from 1 to infinity of this quantity a sub n cosine nx plus b sub n sine nx for every x in negative pi to pi. The reason why a naught is multiplied by 1/2 is purely technical and it's seen below. Alright, so we've kind of read this section before, and it reminds me that I've been reading this other book from this university mathematical text series. I tried to collect as many of these I can find because they're all the same form factor, and they're all quite good, and they're from people who are like in the FRS or have DSCs, and so it's from Cambridge and Edinburgh and this kinds of things back in the 40s and 50s. Anyways, that one's on wave motion, the mechanics of wave motion, and it has a lot going on with regards to the sinusoidal, of course, and it interested me about the Fourier series when you find certain expressions that reflect the parametric forms of these things. And then they start to have names, and for example, the amplitude of a wave, or that 2a is the same period as 2 pi, or that the sine and cosine are so as normalized, or that it's reduced to a different particular range of the things about in the angular when things are in the radians, and with regards to usually in the real numbers when they're in regular units. That hereafter, having read a bit about this Fourier coefficients, a similar procedure that the a sub n's are defined by 1/pi, integral from negative pi to pi of fx cosine mx dx for this function, and for b sub m, it's 1/pi times this integral from negative pi to pi of fx sine mx dx. So that makes it so. Then the idea is then to figure out for all these sorts of integral equations, what's possible to make for all these sorts of orthogonal functions, the families thereof, all possible ways to make a series of them via means to compute thusly their coefficients. And then to figure out, especially when those coefficients can be determined to have forms that define them, closed forms, whether there be polynomials or expressions in choice numbers or Stirling numbers of the first or second kind, or Bessel's function, or various polynomials, any one of these special integer sequences. For example, this would probably be cataloged somewhere in the online encyclopedia of integer sequences, as from N.J.A. Sloan and Company, which is a great resource that has pretty much every integer sequence that's ever been deemed interesting. Its first many elements, and thus they can be searched and kind of found. For example, the sums of consecutive cubes, and the fact that then among those there's a very high density of primes called the cuban primes, of those being otherwise the hexagonal numbers that are also so formed by these kinds of things. That there's all these kinds of different numerical relations in the integer series that make for then when the expansions occur like so, that the coefficients can be determined in terms of these integer series, or and those are various just functions or formulas, or as was discussed about the classical orthogonal polynomials that kind of complement these orthogonal functions, which have the means to treat each section of the area as having a contribution that's only limited to that piece to make up a mensuration in effect about it. That these are the kinds of things that then go on to, as from the previous talk, the idea of using this trilateralometry or n-gonometry to determine what functions those chart, and then otherwise the analytical properties of those functions in the higher order. If, for example, one of these square functions can be offset into 3 different pieces, or so on, or 7 and 6, or something like that. The idea being that just as that the trigonometry after Pythagoras' theorem and right triangles makes it possible to compute these things as about the circle, it's also possible to just compute them as about the line. And for a line segment, even just that it flips over and then it flips under and flips over and flips under and ... that it draws a periodic function that's just like this half circle waves. That's not really so otherwise usually defined as a formula, because cosine and sine are smooth and continuous functions, and they were built from the beginning to model all these different aspects of the wave motion. That is almost that kind of thing is the bit simpler, and so it's to be figured out why it's what it's missing basically, and then to augment it, to provide it, to equip it with what results then that it makes an analytical basis for these other frameworks, that then eventually when you find things that naturally fit it best, that it's the smallest closed form, and this is the most efficient, the highest performance. So back into the Fourier series and just kind of scanning along. The simple method was devised by Leonhard Euler in 1777, but only after having first obtained these formulas in a more complicated manner. Fourier arrived at the same result independently, also discovering the simple method after a much more complicated one. So getting into the reasons why there are these simple and complicated methods, we'd probably look to the means and methods available to these students, these researchers, and what they would have had available in terms of the numerical analysis at the time, with regards to, who knows, Simon Steven, or otherwise the Bernoulli brothers, or what was available to Leonhard Euler, who was held up in very high regard, and that later he was followed on by Gauss, basically, and then after Gauss's Disquisitiones where he collected all these different and interesting things, that it was something to be figured out about the Gaussian analysis, and that expresses a whole framework of opinion, that some things that they might have been more complicated, what they started with, might be more necessary and relevant for these deconstructivist accounts. That what's been built up in the complex and the Gaussian analysis, that after the linear and the exponential and the hyperbolic, for these usual families of forms of what make most of the differential equations of interest, and the way that gets into this Gaussian integral and its complex form, and then e to the negative I pi, and using that form to make up some rules for arithmetic, and then figuring out how that works up, that ends up almost that the complex analysis seems to be a little bit contrived sometimes. And then instead we might want to start with something for complex analysis like the roots of unity, and to figure out then a deconstructive account of the the e to the I pi equals -1 or whatever it is. With regards to that, while it's pretty interesting and beautiful and all this kind of stuff, but then it ends up with some funny things like, well, now you can just add up this series and get a real number out of it, like -1/12, the -1/12 result, and how that's arbitrary and that's capricious, and it essentially just represents an opinion of a sort with regards to otherwise that it coming and going in the same framework kind of results that it cancels itself out or drops itself out. But there would be other ones that would have more real analytical character. So here the approach to that has kind of been to even just deconstruct that further and start with building the dimension of the one-dimensional from the two-dimensional, calling x and y the two dimensions, the semi-dimensions, and that those co-semi-dimensions result a dimension in the identity dimension, or xy, and then building on the analysis in terms of the line already that's defined these other ones, so that then things that are formed as about it kind of have these coordinates of a box about it, basically. So it makes for making a box about it, and in some sense then for the circles centered on the identity line, the ability to consider lots of different ways that I'm thinking can go into making a lot of different analytical methods pretty simple as of above about √2, and then in the higher dimensions as of about the solutions for the roots of unity, and getting into these kinds of things. The Fourier coefficients are these a sub n and b sub n, and the series 1/2 a naught plus some 1 infinity a sub n cosine nx plus b sub n sine nx. It's called the Fourier series, and there was described the tilde or it equals or approximates, and then finding where it's so. And this was sort of read before, so I haven't quite got up to the bookmark yet. But reading into this book with many chapters and things on it about that. Oh, is that then we got into the Riemann-Lebesgue theorem, the Riemann-Lebesgue integration, when last we were talking about the Fourier analysis. And so here we'd already been talking about the this identity dimension bit, and figuring out a simple integration about some of its contents, or for writing in terms of that coordinate space and its metric and this kinds of thing, and the coordinate space and the metrics is to and from it, in a sense. Figuring that might be a particularly tractable way to get when you have two different coordinate spaces and metrics, then trying to figure out even at all how to transform back and forth between them is both very flexible and useful and powerful, and the substitution of variables and composition of functions makes for many great things, and the chain rule and the transitivity and these kinds of things that make it possible to derive results based upon a chain of things and a substitution of things. And then these transformations of coordinates then get into sometimes that's really simple and tractable, and sometimes it's not. And then when it gets into whatever other reason means that there can be, that you can basically define the origin and then a parameter called the coordinate, and then about the ordinate and the abscissa, where these values of these vectors in, say, what's look like a vector space maybe drop to the line or drop to or fall to the axis, or as it were. These become then means to fill out these sections. And so that's something I've been thinking about, even just from the origins of the fundamental theorems, how to make it so arrive at what are some of these underexplored these days means that these would have just as well and as simply be what would have been more explored in the antiquity, because that's where it would start in the very fundamental and the very deconstructed, in terms of then that when we already have all this luxury of the richness of the whole number system, the entire number system, and all these formulas and everything kind of put together for us and provided as a finished whole, as it were, or an entire thing. There are all the moving parts underneath it, and then that some of the generality of the overall results that keep everything so tractable in this entire milieu would be unavailable. Still makes for that then, if it's possible to figure out some kind of coordinate system and metric space between this quadrant and octants, and kind of treating anything that you might imagine as kind of just a useful feature of going to the Argand or Wessel plane, or for that matter even just useful features of having symmetry about positive and negative numbers and computing roots and these kinds of things. Similarly would follow from this sort of reducing the problem to only the positive numbers and having an identity, and with that having an origin and it having an infinity, so that then this line is staked out with kind of the entire notion that it grows and comes back to zero, and then figuring out how to treat even the entire ultimate scale of shrinking the box, the entire quadrant would point out to infinity, and then being able to deal with how that would be, so even if it was just a bounded case and very large, that even if we don't have actual infinity, there's still potential infinity, and it can be built as an effective infinity in the numbers, and that it already exists and lives in these differential systems also, then makes that all the way that any of these differential systems play in the quadrant themselves will be how they draw themselves on the line. And so it becomes a thing about when they do and don't approximate the linear, or they're on the order of it. So quoting the author, Dirichlet knew that he had introduced the requirement of continuity. Dirichlet needed is what Cauchy's definition did not provide, namely a condition for integrability. So here we've reached the bookmark about the Riemann and Darboux. Riemann's definition was perfected in 1875 by Jean-Gaston Darboux, the man responsible for the dissemination of Riemann's ideas in France, who also proved the corresponding version of the FTC, the fundamental theorem of calculus. In modern terminology, this definition, which we shall need later, can be introduced as follows: that x naught xn be points in AB, and this section has been read already, such that A equals x naught less than less than xn equals B. So between A and B, there's these points, and they're in order and by their indexes and the real numbers between A and B, inclusive. Such a collection of points is called a partition of AB. Then for I between 1 and n, inclusive, define m sub I to be the smallest real number that is not smaller than any value of f on x I minus 1 x sub I. Of course, if f has a maximum on x I sub 1 comma x sub I, then m sub I is this maximum value. Similarly, let m sub I be the largest real number that is not larger than any value of f on x I minus 1 x I. If a function from a to b, the interval onto R is a bounded function, then it is said to be Riemann integrable, or simply integrable on a, b, if and only if there's unique number 1 such that, or unique number L, I imagine that must be, I equals L to n, m sub I, times the quantity x I minus x I sub 1 less than equal to L, less than equal to I equals sigma from 1 to n of big M sub I, the quantity x sub I minus x sub I minus 1 for every partition of AB. This number I is called the Riemann integral of f from a to b and is denoted by the integral of a sub bf. Now this is basically the same as saying that there's no vertical line. That it's a continuous function and that it has no vertical asymptote. And it's kind of an equivalent definition. Then it gets into what is not easy to determine through direct application of this definition is whether or not a given bounded function is Riemann integrable. A simple criterion for integrability was given by Lebesgue in 1904 on the basis of the following concept. A subset of R is said to have measure 0 if and only if it can be enclosed in a finite or infinite sequence of open intervals whose combined total length, the sum of a finite or infinite series whose terms of the lengths of the individual intervals, is arbitrarily small. That is smaller than any pre-assigned positive number. Then Lebesgue showed that f is Riemann integrable on AB if and only if the set of points where f is discontinuous has measure 0. So this being about the discontinuities, you can otherwise always, kind of deal with the discontinuities as piecewise, and then so that in A sub b, if there's any region that's not Riemann integrable, you can always just exclude it and then figure out some other means for it. For example, if it's measure 0, to ignore it. But it is clear in particular that a bounded continuous function is integrable on AB that has no vertical lines in it. A type of integrable function with discontinuities that is frequently encountered in the applications is as defined as follows. The piecewise continuous. And so the piecewise continuous is just from left to right, treating each partition of the real numbers as a region that's the entire contents between the left and right boundary of it, and vertically the entire range in Y. Each of those is a piece, and that the limits to the left and limits to the right of those match up together, regardless then of whether that they are the same. Because this continuous function as well needs to be smooth in a sense. It has to have a formula, and then as to whether it has a formula that so defines it, I guess this is a pretty general definition for the integrability conditions.